Hello, I am Sapna Davis of EC Department, Rajagiri School of Engineering and Technology. Support vector machines, these are also called as maximum margin classifiers. Consider the two-class classification problem using linear models of the form yx equal to w transpose phi x plus b, where phi x is the feature space transformation and b is the bias. Training data set comprises of n input vectors x1 to xn with the corresponding target values t1 to tn. Tn can take values -1 and 1, and new data points x are classified according to the sign of a yx. Assume training data set are linearly separable in feature space, then at least one choice of W and B gives a yxn greater than 0 for input data with Tn equal to +1 and yxn less than 0 for Tn equal to -1, so that Tn yxn will be greater than 0 for all the training data points. In support vector machines, the decision boundary is chosen to maximize the margin. Margin is the smallest distance between the decision boundary and any of the data samples. The data points which are closest to the decision boundary are called as support vectors and indicated by the circles in the figure. Maximizing the margin leads to a particular choice of decision boundary. Red line shows the decision boundary and blue lines indicate margin boundaries, and support vectors are lying on the margin boundaries. The perpendicular distance of a point x from a hyperplane yx equal to 0 is given by magnitude of yx division length of w. Consider data points xn which are correctly classified so that tn yxn greater than 0 for all n. Then the distance of xn to the decision surface is given by tn yxn division length of w. The margin is given by the perpendicular distance from decision surface to the closest point xn. Now we can optimize the parameters w and b to maximize this distance. Thus, the maximum margin solution is found by solving for the maximum value of the perpendicular distance. Now we can set T and W transpose phi xn plus b equal to 1 for the point that is lying closest to the decision surface. Then all data points will satisfy the constraints. T and W transpose phi xn plus b will be greater than or equal to 1. And this is known as the canonical representation of the decision hyperplane. The optimization problem is to maximize 1 by W, which is equivalent to minimizing W square, and so we have to solve the optimization problem for minimizing 1 by 2 W square subject to the constraints T and Yxn greater than or equal to 1. The factor 1 by 2 is included for later convenience. To solve the constraint optimization problem, we can introduce Lagrangian multipliers an greater than or equal to 0, giving the Lagrangian function L of WBA equal to 1 by 2 W square minus summation n equal to 1 to n an tn W transpose phi xn plus b minus 1, where a equal to a1 a2 an transpose. Setting the derivatives of L of WBA with respect to W and B equal to 0, we obtain W equal to summation n equal to 1 to n an tn phi xn, and also summation n equal to 1 to n an tn equal to 0. Eliminated W and B from L of WBA using these equations gives the dual representation of the maximum margin problem. We get L of I equal to summation n equal to 1 to n an minus 1 by 2 double summation an am tn tm k of x and xm, subject to the constraints an greater than or equal to 0, and also summation n equal to 1 to n an tn equal to 0. Here the kernel function is defined by k of x dash equal to phi x transpose multiplied by phi x dash. To classify new data points using the train model, we evaluate the sign of yx. Yx in terms of an and the kernel function is given. The constraint optimization satisfies the KKT conditions an greater than or equal to 0, tn yxn minus 1 greater than or equal to 0, an tn yxn minus 1 equal to 0. The data points that satisfy T and Yxn equal to 1 are called as support vectors, and they correspond to points that lie on the maximum margin hyperplanes in feature space. Once we find a value of threshold parameter, B can be found from any support vector xn satisfying Tn y xn equal to 1. In the equation, S denotes the set of support vectors. The equation for B is given. Here Ns is the total number of support vectors. The maximum margin classifier can be given in terms of the minimization of an error function of the form summation n equal to 1 to n e infinity of yxn tn minus 1 plus lambda w square. E infinity of z is a function that is 0 if z is greater than or equal to 0 and infinity otherwise. This ensures the condition Tn yxn greater than or equal to 1. SVM for overlapping class distributions or not linearly separable case. If the training vectors are linearly separable in the feature space phi x, SVM gives exact separation of the training data in the input space x. Decision boundary may not be linear. In practice, exact separation of the training data can lead to poor generalization. So we can modify the SVM so as to allow some of the training points to be misclassified. That is, data points are allowed on the wrong side of the margin boundary. To do this, we introduce slack variables theta n greater than or equal to 0 where n equal to 1 to n. That is one slack variable for every training data point. Theta n equal to 0 for data points that are on or inside the correct margin boundary and theta n equal to magnitude of Tn minus yxn for other points. Thus, a data point that is on the decision boundary yxn equal to 0 will have theta n equal to 1 and points with the theta n greater than 1 will be misclassified. The classification constraints are then replaced by Tn yxn greater than or equal to 1 minus theta n where theta n greater than or equal to 0. Data points for which theta n equal to 0 are correctly classified and are either on the margin or on the correct side of the margin. Points for which 0 less than theta n less than or equal to 1 lie outside the margin but on the correct side of the decision boundary, and those data points for which theta n greater than 1 lie on the wrong side of the decision boundary and will be misclassified as shown in the figure. This relaxes the hard margin constraint to give a soft margin and allows some of the training data points to be misclassified. Now our goal is to maximize the margin while softly penalizing the points that lie on the wrong side of the margin boundary. We therefore minimize C summation n equal to 1 to n theta n plus 1 by 2 w square. The parameter C greater than 0 controls the trade-off between the slack variable penalty and the margin. Any point that is misclassified as a theta n greater than 1. So summation theta n is an upper bound on the number of misclassified points. The constraint optimization problem is represented by the Lagrange function as given. The corresponding set of KKT conditions are given. Now optimizing W, P and theta n, we obtain W equal to summation n equal to 1 to n a n t n phi xn, summation n equal to 1 to n a n t n equal to 0 and a n equal to c minus mu n. Using this eliminated W, B and theta n from the Lagrangian, we obtain the dual Lagrange function as given. This is identical to the separable case except that the constraints are different. Now a n equal to c minus mu n and mu n greater than or equal to 0 implies a n less than or equal to c. We therefore have to minimize L of a with respect to the variables a n subject to the conditions. A n lies between 0 and c and summation n equal to a n t n equal to 0 for n equal to 1 to n, and these are known as the box constraints. Replacing W, predictions for new data points are given by the equation. A subset of the data points may have a n equal to 0 and they do not contribute to the predictive model Yx. The remaining data points constitute the support vectors and hence must satisfy Tn Yxn equal to 1 minus theta n. To determine the parameter B, the support vectors will satisfy Kn summation am tm kxn xm plus b equal to 1. Solution for B is given. Here M denotes the set of indices of data points having 0 less than a n less than c.